welcome to today's webinar. My name is Nick Herringer. I will be your host, and today we will be discussing methods for stray light analysis in OpticStudio. So to give you a brief introduction and overview of what we'll be talking about today, we'll start with an introduction to stray light, kind of learn how to talk about it, learn some basic definitions, and then we'll get right on into looking at some of the tools that we have built into OpticStudio that allow us to quantify it and identify its sources. If you are new to stray light analysis, this may be a lot of information. So we would encourage you to check out some of the resources that we have on our website, including our knowledge base, which you can find at this address right up here in the top right of the screen in yellow. Specifically, we have the illumination and stray light and thin film coatings sections, which have some pretty good articles which describe the processes that I'll be talking about today. And then also we have some training courses, including specifically this lighting and illumination design course, which looks at using OpticStudio in non-sequential mode. And as part of that, we discuss and talk about stray light analysis. And you can find our training courses on our website as well at zmax.com/zmx/training/courses. To give you a more comprehensive overview of specifically what we'll be looking at today, we will start by asking the question, what is stray light? To give us a base from which to grow. Then we'll be looking at the tools that OpticStudio has that allow us to analyze stray light. These include converting to non-sequential mode or non-sequential groups, the 3D layout and shaded models, filter strings, applying coatings, and then using the ray database viewer and path analysis to see exactly where our rays are going in our system. And then at the very end, before I let you go, we're going to introduce Lens Mechanics, which is our new software, and how that can take stray light analysis a step further by easily integrating mechanical components and allowing a good dialogue back and forth between the two pieces of software so that whole teams of optical and mechanical engineers can continue to refine their designs, specifically in a stray light analysis world. So, stray light in itself refers to unwanted light in an optical system. Generally, it takes three forms. These are ghost images, scattering, and straight paths from outside the desired field of view. Ghost images are out of focus images of bright spots such as the sun, and these are caused by unwanted reflections off lens surfaces as light passes through the system. Scattering can cause light to take unexpected or unwanted paths through the system, and this plays a huge part when we have mechanical components. And then straight paths from outside the desired field of view often result or can result from improper design or improper baffle placement in your system. All right, so let's get right on into an example. So today we'll be using a riff on the double Gauss 28-degree field sample file that we ship with OpticStudio. This is a really standard file, and it's one that we here at ZMax like to refer to a lot because it has a lot of good applications. I say that this is a riff on the sample file because in the file that will be attached with this webinar, after we post it on our website, all of the surface coatings have been removed. One thing you'll notice just with where this sample file is coming from, it is our sequential folder of the sample files. So that means that this folder or this file starts off in sequential mode. However, we will need to do a conversion to non-sequential mode for us to perform stray light analysis. So that's going to be our first step. We have a very convenient tool built into OpticStudio that allows us to really easily convert from sequential to non-sequential mode, and that is the Convert to NSC Group button. So we'll be using this today to change our file. We'll basically take the sequential surfaces in it and convert them to their non-sequential equivalents. Before we do this, we'll want to lock down our design, which will remove all the solves, apply apertures to the semi-diameters, and fix the system so that nothing changes as we convert the system as a whole. So let's look at OpticStudio and actually go over how to do this. So here I have our sequential system. You can see that this is simply a rearranged double Gauss sample file, and I have removed the coatings here in the coating column. So none of these lenses have coatings on them. So if we want to convert this to non-sequential mode, we just go up here to the File tab, Convert to NSC Group, and we can click right into that. Now, like I mentioned, we want to lock down the design. So I'll move this over here, and you can see what happens when I do this. So if we lock down the design, this will remove all the solves and convert all of our surfaces to have apertures. So I'm just going to click OK. I don't need to save the new system. And when I did this, you can see that all of the variables over here were removed, as well as surface apertures applied to all of these surfaces. So now if we want to complete the conversion, I will not be saving this as a new system, so I will uncheck this. I will add sources and detectors for the whole system, and we'll convert the file to non-sequential mode. If we leave this unchecked, it'll convert the surfaces defined here to a non-sequential group, which you can use in mixed mode. But here we'll be converting to pure non-sequential, so we'll go ahead and convert. So as you can see, we now have 3 sources, 1 for each field of view. We have all of our standard lenses, which were converted from standard surfaces in the previous file. We have an image plane, and then we have 4 detectors, all placed at that image plane. Objects 12, 13, and 14 correspond to fields 1, 2, and 3, the focuses there. And object 15 is our full field detector. So I'm going to make some small changes to this system before we actually go ahead and start doing some straight line analysis. For speed's sake, I'm going to change the number of analysis rays for each of our sources to 10,000. I'm going to change the sampling method for our sources to random. So that's in the Properties, Sources, Ray Trace settings. I'll do this for each of them. The reason for this will be more clear as we go along. And then last but not least, I'm going to set the material for all of our detectors to absorb. Now what I'm going to do is look at a shaded model or a 3D layout for the system. So here it is. That looks very standard, just what it looked like in sequential mode. However, what we're going to do now is turn on splitting. So we're going to split our NSC rays with this checkbox here in the properties. And you can see very quickly that our layout becomes very chaotic. And this is not something that is very conducive to performing any sort of analysis because we can't really see where any of the rays are going here. It just looks like a big blob. So how do we actually then get into performing the straight light analysis? Well, I'm going to first lock down this window, and we'll save it for later so we have something to compare to. So how do we actually then start doing our stray light analysis? Well, what we're going to do first is just run a ray trace. So here we go. I'm going to make sure to split the NSC rays in the trace. Notice that use polarization also gets checked by default or automatically when you check split NSC rays. I'm also going to save the rays as a Zmax ray database or a .zrd file. And we'll discuss that in more detail later. So let's just run that. Should go pretty quickly. All right, so we have completed our ray trace. We'll exit there, and we'll look at the results in a detector viewer. So that is right up here in the Analyze tab, Detector Viewer. We'll need to configure this. to look at our full field, so detector 15. We're going to go false color and a log scale as well. And then we're also going to apply the ray database that we just saved, which is this one right here. All right, so there is all of the light that is reaching our detector, but we only want to look at stray light that is reaching our detector. So we'll save this for here, and we will look back at our presentation and talk about one method for isolating rays on our detector viewer. So that method is called filter string. And filter strings allow users to isolate certain rays by defining tests which rays must pass. You can apply filters to layout plots, detector viewers, array trace, and even the path analysis and ray database viewers, which we'll talk about later. In addition, filter strings can be really useful because you can connect them with logical operations. And then we also have numeric arguments that are supported for what we call extended flag filter strings. The logical operands that are built into OpticStudio are the logical AND, the logical OR, the exclusive OR, and the logical NOT. So looking at each of those, the logical AND returns true only if the filter strings on either side of the AND symbol are true. Logical OR returns true if either string is true. Exclusive OR returns true if only one of the strings is true. And the logical NOT returns true if the string to the right is false. With these, you can use parenthetical hierarchy to set operator precedence. So looking at some examples of filter strings, you can see if we would like to isolate rays that hit object 7 and 10, but did not reflect from object 6, or missed object 15, we would use a filter string as it is here, where we have hit 7 and hit 9, but did not reflect from object 6 in parentheses, or array that missed M15, object 15. And similarly, to isolate rays that either hit objects number 5 or number 7, or missed object 5 and either reflected from object 6 or object 7, we would use this filter string here. So let's apply some filter strings to our system and see how things look. So what we're going to be doing here is using filter strings to isolate the problem rays, specifically ghost reflected rays that make it through to our detector object 15. So the filter strings that we're going to be using are GN and HN. G for ghost, N for the object number, H for hit, and then N again for the object number. So these will return true for a ray that is ghost reflected from object N or hits object N. So if we look into OpticStudio, we can unlock this window first and apply a filter directly to our ray trace. So here what I'm going to do is type in the following filter. So G0 signifies rays that are ghost reflected at any object, and H15 isolates rays that hit object 15. So applying these together, we'll get all ghost reflected rays that hit on object 15. So let's apply that, and then we'll lock down our system again. So we can also look at how these rays compare to our original 3D layout by opening another one and applying a filter string there. So we're going to turn on splitting, and we'll add our filter, and we'll apply. And comparing this to our original 3D layout, we can see that we have definitely simplified the rays in our system. It is less chaotic. We've narrowed our scope. So let's dock this back down and keep analyzing. So now we want to see which rays are causing the most problems. And how we're going to do this is open our non-sequential portion of the System Explorer we're going to increase the minimum relative ray intensity from 1 e to the minus 6 to 1 e to the minus 2. So what this is going to do is only display arrays that are more powerful or have more energy associated with them. So all of the relatively weak rays will be eliminated from the shaded model. Then what we can do is update our shaded model several times and see, generally speaking, where these powerful rays are landing. So here you have a relatively good representation. We have one ray from each field. We can see some reflections occurring here on our last lens element, here on this surface. We can see that there are a lot of reflections here. So these surfaces then, we may be able to consider these surfaces as our problem surfaces. And we may be able to resolve or eliminate the reflections from these surfaces by making some changes to our system. What we're going to do here is apply a coating to these surfaces, specifically anti-reflection coating. So coatings can be used to reduce reflection losses, polarization aberration, dye-attenuation, and retardance in a system. OpticStudio can model thin film coatings, including uncoated substrates, singular multi-layer coatings, coatings on mirror, as well as several others. We model coatings in several different ways. These include, or the four coating categories that we have in OpticStudio are ideal, layered, table, and encrypted coatings. Coatings are stored in the coating file, which is accessible in the File tab, which is accessible in the Libraries tab under Coating Tools, as shown up here. And it is recommended that if you're ever going to add a coating or change coatings in the coating file, that you don't edit the original file. Always save your changes in a new coating file. That way, when you upgrade from one version of OpticStudio to the next, they are not overwritten with a new default. And you can change the coding file that you're using in the software from the System Explorer. So like I mentioned earlier, here we'll be applying some single layer anti-reflection coatings, which are already saved in the coding file. So when we apply coatings in OpticStudio, we do so on the different faces of an object. And you can access these faces in the object properties. So in our case for this system, what we're going to be doing is applying an AR coating to the front faces of objects 4, 5, 8, and 10, and to the back faces of objects 4, 6, 9, and 10. So let's go back into OpticStudio. Let's open up our non-sequential component editor, and we will start out object 4. To see which face of the object we would like to apply coatings to, we can use this View Current Object button. If we open the Object 4 properties here, go to Coat and Scatter, we can see this face field here. As we select the different faces of our object, we'll see that the object viewer over here changes which face is orange or highlighted. As we tab through our objects, you can see that the objects themselves change. So let's start applying coatings to these faces. So we are applying both to the front and back of object 4. So we have the front face selected. We'll go down to this coating dropdown and select AR or anti-reflection. We'll do the same for the back face. You can see here that the back face is highlighted. And then I will go through and do the rest of our surfaces. And there we go. So we now have coatings applied to all of our objects. We can reduce the properties there. We can close out our object viewer just to clean things up on our window. And now what we're going to do is reanalyze the system. To do this, we're going to set the same parameters that we had before here, minimum relative ray intensity, just to make sure our results are consistent. Then we'll run another ray trace. And this time we're going to change the ray database to be titled the same thing, but with coatings tagged onto the end. We will clear and trace. And that's completed. So we'll exit out. And we will open up a new detector viewer. We'll make the settings the same, load in our new ZRD file, and we'll apply our filter. So we can compare our results now and see that we have significantly reduced the contributions of stray light due to ghost reflections in our system. If we look down here at our original ray trace results, we can see that we had about 2.1 times 10 to the minus 2 watts on our detector. If we look at our new results, we can see that we have about 4.8 times 10 to the minus 3 watts. So we've reduced the power recorded on our detector by almost a factor of 10, which is pretty darn good. So that shows that those coatings that we added made a significant improvement to our system as a whole in terms of stray light. We've obviously done some very good things here, but we can definitely keep improving this system. So let's keep analyzing. So now what we're going to do is look at another two tools we have, in fact, called the Ray Database Viewer and Path Analysis. And so what these are both going to incorporate, much as our detector viewers have so far, are these Zemax ray databases that we've saved when we run our ray trace. So as a disclaimer here, I'd like to let you know that saving rays can significantly slow down your ray trace. And if you have splitting or scattering on when you run your ray trace and save it, ray databases can grow in size very quickly. So you need to make sure that you have enough storage on your machine. Because if you do not have enough storage on your machine, you will not be saving all of the results from your ray trace, which may give you skewed data. Looking at what the ZRD itself actually contains, we have the segment number of the ray, starting from 0 at the source, or to the total number of segments the ray can generate. We'll have in signifies the number of the object the ray is traveling through. We record the number of the object struck at the end of each segment. If the object hit is 0, then the ray missed all objects and is terminated. We have the face of the object, which can be very important for stray light analysis, or that is which face of the object the ray segment intersected. And then we also have some information down here in this XRTS DGEFBZ code. And this describes what happens to each of the segments. So that is, was it terminated, was it reflected, was it transmitted, scattered, etc. Each of these terms corresponds to one of those results. And we'll see that when we open the Ray Database Viewer shortly. To give you a brief overview of the Ray Database Viewer, this displays all the data for each of the rays in the ZRD. So it allows us to look in really great detail where each ray is going and what it's doing at each of its surfaces it intersects. However, this can be a ton of information. So you need to be selective and careful about how you use it and how you filter within it. If we're trying to get the more broad strokes, we can use another tool called Path Analysis. And this categorizes ray paths themselves based on specific criteria. So that's the total ending flux for all rays that take a given path, the number of objects those rays strike during those paths, the number of branches, the last object struck, and then the number of unique objects struck. So it's a more general description of groups of rays, and it categorizes each possible path. And this makes finding and visualizing the most problematic paths very easy. And again, this can be used in conjunction with filter flags. We'll get to using path analysis in our example shortly, but I'd like to give you a brief description of some of the filters we'll be using so things make a little more sense. Like we have been, we'll be looking again at ghost rays on our detector. And what we're going to notice is that we have a small patch of rays hitting the bottom portion of our detector. So we're going to isolate that area using the following filter strings. These are essentially boundary conditions on the X and Y coordinates. So we can specify a max and a min and isolate a rectangular region on our detector. When we isolate these rays, we can see exactly where they're coming from and all the paths that they follow. And in the 3D layout, this is again a lot of information and maybe not the most helpful information. So what we can do is use path analysis to isolate the most problematic ray paths. And we're going to see that one group, one path in particular, contributes far more than the rest. So let's get into actually doing this example. So as you may have noticed in our slides, we had changed the maximum intersections per ray and maximum segments per ray here in the System Explorer. And what we're going to do is adjust these to 4,000 and 2 million respectively. This will just give us a much more comprehensive analysis of each of the ray paths. So to clean things up, I'm going to minimize the windows we have open. All right, so now we're going to run a ray trace. And we're going to save this ray database as paths, and we will trace those. So when our ray trace is completed, we'll exit, then we'll open up a detector viewer to see how things look. Here we'll be dealing with some more powerful rays, so we will not go to a log scale. And as I mentioned, we can see down at the bottom of our screen here, we have this small patch of rays that are making it through our system and are still being ghost reflected. So what we're going to do is isolate those in our 3D layout. So let's apply the filter string here. So here's our filter string. We're looking at x coordinates greater than -13, less than +13, greater than -50, and less than -46 that are also ghost reflected and hit object 15. So let's apply this. We need to remember to put on ray database. So our filter string here will look at arrays that land at x coordinates greater than -13 but less than 13, and y coordinates greater than -50 and less than -46, but are also ghost reflected and hit object 15. We need to make sure to add our paths ray database and add splitting on our 3D layout. And here you can see all of the paths that hit down in that small region at the bottom of our detector, right down there. But again, this layout is not the most helpful. So we can look at these other tools, including the Ray Database Viewer, which will turn out to also not be the most helpful, as we can see that we have tons of information here. But as you can see, we have all those bits of information that we talked about earlier, including the XRTS, DGEF, and BZ flags here, indicated true if it has a star or an asterisk. So rather than look at this, we're going to look at our path analysis. And here, we are going to apply that same filter. For speed's sake, I will simply copy it from here and paste it in. We will also make sure that this generate path filters flag is checked. What this will do is allow us to filter paths from path analysis in our 3D layout and detector viewer. So after we've done this, we'll notice that we have all of the paths listed here, and we can see how many total paths we have. So here we have 146 total paths that return true for this filter string. We can see the total flux for each of those paths and what percent of the total flux of our entire system those rays represent. So we can see here that we have a lot that are very, very, very small and almost get down to nothing towards the bottom of our list. But at the very top, we have one path that contributes 0.8% of the total energy on the detector. So what we can do is isolate this path in our layout and see exactly where it's coming from. And we can do this by adding the filter string _1 to our 3D layout. and we'll apply that. All right, now that that is done, we will reset our zoom to YZ, and we can very quickly see something strange about this path, and that is that the rays that follow it actually miss our first lens and are reflected off of our third lens element right here. So one thing that we can do to make sure that these rays do not enter our system, are not registered on our detector, is actually add some mechanical components to our system, a lens housing, for example. And these lens housings are very easily added in the new software that we've developed called Lens Mechanics. So this will allow us to work with a mechanical engineer to design some sort of housing like this, as well as other components, spacers and such for the lenses to hold them in place. And it will allow us to have them build these objects and very easily import them back into our optical design in OpticStudio. Now, part 2 of this webinar series will talk about how we actually create those housings in lens mechanics, and then how we can integrate the design, the lens mechanics designs, with the OpticStudio design to continue using stray light analysis to optimize and refine our system. With this, we can look at applying scatter functions to those mechanical elements and perform ray traces both in lens mechanics and OpticStudio to make sure that we're not compromising our design at any point along the way and getting the best results that we possibly can. So stay tuned, because this will be the next portion of this webinar. So to give you a summary of what we discussed today, we first went over how to convert to non-sequential mode. We then applied some filter strings and discussed some of the capabilities of them. We applied coatings to reduce ghost reflected rays on some surfaces in our system. And then we used path analysis and very briefly showed the Ray Database Viewer and how we can use them to analyze ray paths in our system and identify which ray paths may be causing problems. If you'd like some more info on stray light analysis in OpticStudio, definitely feel free to check out our knowledge base. We have the illumination and stray light and thin film coating sections. You can also check out the help files for any of the features we looked at today. And then, as I mentioned before, our newly updated training courses, specifically the lighting and illumination design course, which you can see a brief description of here. So thank you again for attending. We will be having a brief question and answer session in just a few minutes. For right now, we will take a quick break. Feel free to send in your answers via the GoToWebinar control panel, and we will commence that shortly. If your questions don't get answered, feel free to send us an email at feedback@zmax.com, and we will answer your questions there. So thank you again, and we will be back in just a few minutes to continue our question and answer section.